Let's talk about the big glass that astronomers are building for a next generation of telescopes. The LSST mirror is sturdy enough that you can sit on it, as you can see in this picture. Also, it's huge. It's the size of your living room or larger. Not just telescopes on the ground, but telescopes in space are attaining new heights. The frontier for space astronomy will be the James Webb Space Telescope, the successor to Hubble. Time and cost overruns mean that the Hubble will die before the James Webb Space Telescope is likely to be launched. But James Webb will eclipse Hubble in its size, being 6.5 meters in diameter. James Webb is an extremely challenging design. The mirror will essentially unfold once it reaches its location 1 million miles from the Earth. This is so far from the Earth it is unserviceable by astronauts. This telescope has to work perfectly and correctly because it can't be fixed if anything goes wrong. That's very high stakes for a space mission. The mirror unfolds when it's situated at its proper location and the instruments deploy. There's a sunshade and solar panels as usual to get power from the sun. The individual mirrors are hexagonal elements. All of these have been fabricated and have reached their specification. James Webb's instruments have been tested on the ground and in a vacuum in labs on the ground, and all have met their performance specs. The James Webb Space Telescope is almost ready to fly. James Webb vaults space astronomy into a new regime. The Hubble Space Telescope is 2.4 meters in diameter, about as far as your arm span will reach in either direction. The Spitzer Space Telescope, a wonderful infrared facility, is even smaller, less than 1 meter across. James Webb vaults above these two facilities with 10 times more collecting area, and it will indeed see to the dawn of time. In part because light from the distant universe is redshifted, or shifted by cosmic expansion to longer wavelengths, the James Webb Telescope concentrates on a different spectral region than the Hubble Space Telescope. Hubble works in the ultraviolet, throughout the visible range, and into the near-infrared. James Webb will not work in the ultraviolet, and it will only work at the reddest of optical wavelengths. Most of its work will be at invisibly long wavelengths just beyond where the eye can see. The degree of technical challenge of the James Webb mission is extraordinary because of the complexity and number of moving parts of the instrument and the telescope assembly, and the fact that it must be deployed robotically and remotely, far from the possibility of servicing or fixing by astronauts. The engineers involved in this undoubtedly have had sleepless nights worrying about whether their part of the complex mechanism will work as advertised when launch comes. We could hear from a NASA administrator or chief scientist about the James Webb Space Telescope, but I think it comes better from a young person. Anyone excited about the possibilities of space astronomy will recognize that James Webb is an extraordinary mission.
Here are the top 5 reasons why the James Webb Space Telescope freaking kicks ass. It is huge! The total mirror size is 7.5 times larger than the Hubble Space Telescope's mirror. The heat shield is the size of a tennis court. Number 4, it's a freaking transformer. So in order to fit into the rocket, it's super duper folded up, and then when it arrives, it unfolds in like 12,000 different marvelous little ways that could go wrong at any moment, and it freaks me out because I worry about that. Number 3, it will operate 1 million miles from Earth. That's about 4 times as far away from the Earth as the Moon is. The Webb telescope actually orbits the Sun. That's a simplification. It's actually in the relative stationary Sun-Earth Lagrange point 2, which I'm not going to try to explain to you right now. If it screws up, there's no way to fix it. One chance to do it right, or it's a $6 billion piece of space junk. That is tense. Number 2, it will be able to see planets orbiting stars in our galaxy. Individual planets. If the James Webb Space Telescope was 25 light years away, it could see the Earth. It can also determine the chemical composition of planets, and it can peer into stellar nurseries to see planets as they form. And finally, the James Webb Space Telescope can see 13.4 billion years into the past. We will be seeing the first galaxies as they form, the first stars as they form. And guess what? None of this is necessary to life on Earth. None of it's going to help us cure malaria or install a democracy in Egypt, but it is awesome in the truest sense of the word awesome. I'm sorry that there's so many hand gestures in this video. I am feeling very gestury. This is the dawn of everything that we know, and that is increasing awesome, and that is something that I can get behind.
The James Webb Space Telescope will cover all of astronomy, working on topics from planets to cosmology, but it will have a particular impact on two fields. One is the study of distant galaxies. Perhaps the primary focus of James Webb is going to be detecting first light in the universe. This is a time, somewhat over 13 billion years ago, when the very first stars and galaxies lit up in the universe, which was cooling from a thin, diffuse, and almost uniform gas. This is impossible to observe with the Hubble Space Telescope. It simply doesn't have enough light gathering power, and it works primarily in the visible range, not in the near infrared. James Webb will also do work on characterizing exoplanets. Exoplanets had not even been discovered when the James Webb was first conceived of, so this is new science for that telescope. But it will be able to do spectra of exoplanets to try and look for biomarkers, that is, the chemical signatures of life on a distant planet. A very exciting project that is nonetheless extremely challenging even for this large telescope. James Webb is long overdue and over budget, and the price tag has caused some stress to the astronomical community, as well as to NASA, which manages this large project. But James Webb has an almost firm launch date somewhere around the end of 2016 or early 2017. It's passed all of its technical hurdles, and astronomers are starting to anticipate it with pleasure. That's big glass in space. What about on the ground? We've seen some of the examples of big telescopes that are being prepared at the University of Arizona using our mirrors. The largest single dish at the moment is actually a non-steerable optical telescope called the Gran Canary Telescope, built by the Spanish in partnership with other organizations. It's on the Canary Islands where there's a major observatory, and this mirror can only stare at one strip of sky that passes overhead. That allows the mirror and the telescope to be quite cheap, because no large structure is needed to steer around the sky. The next very large telescope to be commissioned, we hope, will be the Giant Magellan Telescope, a partnership between the University of Arizona, the Smithsonian Organization, and a set of private and public universities in the United States. This telescope should be commissioned sometime late this decade. It's going to be built on the Las Campanas Observatory site, where we already have a pair of 6.5-meter telescopes. This visualization of the structure shows the size and complexity, and also the ability to grasp light from across the universe of this wonderful facility. Even larger than the GMT, and in a sort of a friendly competition with it, is the 30-meter telescope, which is being built by the Caltech and University of California consortium. There's a friendly rivalry here, and in fact, the world perhaps could do with a couple of these large telescopes, since there's plenty of science to fuel more than one super large telescope. The TMT will almost certainly be built either in Hawaii or also in Chile. It's a 30-meter telescope, so is larger than the one that we plan, and it will use the mosaic technology, essentially scaling up the Keck concept rather than having single large monolithic mirrors. An animation of the very center of our galaxy shows the importance of having these super large mirrors, with their diffraction limits realized by the use of adaptive optics. If we look at the seeing of standard Mauna Kea sight, which is exceptionally good, there's just a blur where the star cluster exists at Sagittarius A star. This is the dynamical center of the galaxy. What astronomers want to do is track individual stellar motions over a period of years, the motions in the animation, to deduce the mass of the central black hole. Separating out the motions of the stars implies resolving those stars, and when they're a blurry mess, as is seen without adaptive optics, that's impossible. The first step in this progression is the use of adaptive optics on the Keck 10-meter telescope. This goes some way towards resolving a few dozen stars in the galactic center whose motions can be tracked with time. But to go beyond that with a 30-meter telescope and adaptive optics increases the number of probes of the black hole at the galactic center from a few dozen to perhaps hundreds, and these motions can be studied in exquisite detail. When telescopes get very large, astronomers essentially run out of things to call them. The names almost get silly. There's a telescope that originally was called the Overwhelmingly Large Telescope, OWL, and has been renamed the Extremely Large Telescope, which is a project of the European Southern Observatory. a consortium of countries based in Europe whose observatory is in Chile, in the dark skies and high sight just south of Las Campanas Observatory, where our telescopes are located. This project was supposed to be a 100-meter diameter mirror. If ever built at this size, it would rival the largest human objects made, the Great Pyramid at Giza or any of the big cathedrals of classic Europe. An enormous structure. Imagine a mirror the size of a football pitch pointing with a precision of 1 part in 10 to the 7 to any part of the sky in just 10 seconds. A phenomenal undertaking. The reason to do this is the same as the reason to build any large telescope. When coupled with adaptive optics, the 100-meter aperture gives you even better angular resolution, turning a blurred mass of a star cluster into the pinpoint of hundreds or even thousands of individual stars. This exquisite imaging lets you answer scientific questions that could not possibly be answered either without adaptive optics or without a mirror of this size. In the last few years, budget realities have set in Europe as in the United States, and the 100-meter telescope has been descoped to a mere 42 meters. However, the project is not yet fully funded. When built, it would indeed be the largest telescope in the world. Astronomers' hunger for photons to reach even deeper and further into the universe is unquenched. The biggest glass being contemplated in space is the James Webb Space Telescope, which will be a worthy successor to the Hubble Space Telescope when it's decommissioned in a few years. 6.5 meters in diameter, it will search for first light in the universe. Meanwhile, on the ground, telescopes 10, 20, 30, and even 40 meters are planned. Ground-based observatories that will each cost well over $1 billion and will give unprecedented depth and scope when coupled with the technique of adaptive optics.